Hey guys, in this video I want to focus in on a specific type of condensation reaction called an aldol condensation. So from prior videos, we know that an enolate is a negatively charged species and it can attack electrophiles, okay? But what we didn't really realize up until this point is that these enolates can actually react with themselves, okay? They can react with themselves to condensate, specifically if it's a ketone or aldehyde, it's going to condensate into this category of molecule called a beta hydroxy carbonyl. Okay? Now, the final products are called aldols. That's the reason that we have that name, because they're part aldehyde and they're part alcohol. Okay, so that hence the name aldol. Okay, so guys, what I'm going to do here is I'm going to show you the full mechanism for an aldol condensation. And one of the most important things to realize about any condensation reaction is that a big part of getting these questions right isn't just knowing the mechanism, it's knowing how to line up your carbonyls. Because if you line them up incorrectly, you're going to be doing a lot more work and you're probably going to get it wrong. So I'm going to teach you not only just the mechanism, but I'm going to use my years of teaching experience to try to ingrain this method into you of how's the best way to line up your carbonyls so that you can always visualize the product the easiest, okay? Well, the first step, guys, is super easy. All it is that you're using some kind of base, usually OH negative, to pull off a proton and make your enolate. Now remember that enolates have two different resonance structures. There's also a resonance structure with the negative on the O, but we're not going to use that one. For this mechanism, you always want to be using the enolate on the carbon, because that's going to help predict what our product looks like, okay? Now, the reason that we would get an aldol condensation is when you have a base, but you have no, oops, that's not a no, you have no other electrophile. Okay, so I'd be wondering, how would I know that something's an aldol, and how would I know that something is, let's say, a reaction from another chapter? Because there's a lot of reagents that you know now. But guys, if you are forming an enolate without an electrophile to react with, then you know this is going to be a self-condensation, which is exactly what we're going to draw. Okay, so we've got our enolate. Notice that my enolate, I'm drawing it on the left-hand side. I'm always going to draw the enolate on the left. And I don't have an electrophile on the right. I don't have a halide or an acyl chloride or whatever. So that means I'm forced to react with just another carbonyl. Okay? Well, how does that work? Well, I like to call them, there's the enolate and there's the electrophile. Why? The enolate is the one with the negative charge. The electrophile is the one that you're going to attack the partial positive of. Now, this one should not be in an enolate form. You should just draw this the normal way that it was before the base reacted, okay? Now, a few other pointers here. You want to make sure that your enolate is drawn on the left, but that your anion is toward the electrophile, okay? Because you want to have the electrophile and the anion as close to each other. So here, I'm drawing the enolate on the left, but I want to make sure my negative charge is as close to the electrophile as possible, okay? Also, any R groups on it face downwards. And this is going to come up more later. But if I had bulky R groups on that CH2, I should actually face them facing down to clear the way for the electrophile that I'm about to attack, okay? Awesome. Now my electrophile, you've actually got some special rules about that one. The electrophile you draw on the right, okay? Always draw on the right. And you should draw your smallest group toward anion, okay? The reason is because we're going to have to attack with the anion, and it's going to be easiest to visualize if I have my small group close to the anion and my large group away from it, okay? I think that's enough to get going, okay? So this mechanism is going to look like follows, okay? This is a nucleophilic addition mechanism. So my negative charge is going to attack my partial positive. I'm going to break a bond. And guys, I'm going to make a tetrahedral intermediate. Now, it's a big tetrahedral intermediate, I understand. But you still have an O negative with now what groups? Well, now you've got the extra CH2 that's attached here. We still have that H. The H that was here is still here. It's just I'm not drawing it. And then there's the CH3. Okay? Now, this is called a nucleophilic addition mechanism because we're going to protonate the O at the end. We're not going to kick out a leaving group. So we use water or acid to protonate and to give us our beta hydroxycarbonyl. Okay? Because I have a beta hydroxy on my carbonyl. Okay? Now the reason I call it carbonyl is because it could be either a ketone or an aldehyde, just depending on what you started with. Okay? So that's really it. It's a really easy mechanism. It's nucleophilic addition, putting two molecules together. One thing that I always encourage my students to do is to count up your carbons at the end, because the carbons in your product should match the carbons of your original enolate times 2. So my original enolate had how many carbons? 2. So I have 2 carbons here. I'm going to put 2C, right? And I'm adding another 2C, right? So that means that my beta hydroxycarbonyl should have, if I did it right, it should have 4C. Does it? Let's count. 1, 2, 3, 4. Yeah, we did it right. You'd be surprised how many stupid mistakes are made because you miss a carbon or you add an extra carbon. And guess what? Professors are not forgiving on that kind of stuff, okay? You can make a lot of mistakes, but you can't miss carbons because that's just a completely different molecule. All right, guys. So now it turns out that beta hydroxycarbonyls are a little bit more complex. The story doesn't just end there, okay? Because beta hydroxycarbonyls are much easier to dehydrate than a typical alcohol. Now remember, this concept comes from Organic Chemistry 1, where alcohols underwent dehydration reactions. Remember that in a dehydration, I take away water and I get a double bond, okay? Now usually you need heat to do that, or you need a lot of, a very good, strong acid. Like usually it'd be an acid catalyzed dehydration. I know I'm talking a lot, so I'm going to write it here. Usually this would be an acid catalyzed dehydration in order to do this. I'm going to put here usually. Okay? But it turns out that this alcohol, this specific beta hydroxy, is not going to require a strong acid to dehydrate. In fact, it's not even going to require heat. Okay? Why? Because look at the conjugate. Look at what happens, not the conjugate, but look at the product. After you dehydrate, the dehydration product is uniquely stable. Why? Because it's conjugated. So due to conjugation, this double bond is much more stable than a normal double bond. What that means is that it's not going to take much for that alcohol to leave. In fact, it can leave both in acidic environments and in basic environments, okay? In an acidic environment, it's going to leave via an E1 mechanism. So you guys remember that's a carbocation mechanism where you wind up forming a carbocation and doing a beta elimination. In a basic environment, you can't get a carbocation. You would actually react by another mechanism that we're not even going into in this course called E1CB, or E1 conjugate base. Okay? Now the point here isn't for you to draw these mechanisms. That's not my goal right now. What I want you to know is that many times, because this dehydration is so favored, we're going to assume that the condensation product dehydrated on its own without even requiring an explanation, okay? So sometimes you're going to see your professor just write the product as a double bond, as a dehydration product, and you're not going to ask questions. You're not going to say, but professor, why did it dehydrate? Guys, these are going to spontaneously dehydrate because the product is so stable, okay? Now, we do need to know what this product is called. it is, in general, it's a dehydration product, but specifically as two names. One, and most commonly it's called an alpha-beta unsaturated. That's because now we have an unsaturated bond between our alpha and beta carbons. Okay, so alpha-beta unsaturated, keep that in mind. Another really important name for it is an enone. Okay, so an enone just makes sense. It's a combination of alkene and one. That would either come from the ketone or the aldehyde. It's a carbonyl, okay? So that's where we get the word enone from. Both of them are interchangeable. They just mean that it's the dehydration product of an aldol condensation. And many times, for example, when I'm drawing my products for all of my practice problems, I'm always just going to be taking it to the enone. I'm going to be assuming dehydration. And for your sake, if you're watching these videos and you're wondering, what should I do? Should I dehydrate? I would always dehydrate unless your professor says not to, okay? Because like I said, it's so favored that it's just going to happen without a lot of stimulus, okay? Awesome, guys. So that's it for this video. Let's move on to the next one.